Yeshiva University. If you don't know where Yeshiva is, it's in it's like in Manhattan.
Yeah, it's not Israel. Yeah. Much closer. Okay, so I'd like to thank the organizers for having me here, and it's always a great pleasure to come to the ITAMP. So I'll be talking about quantum systems. They have many interacting particles, and these systems, contrary to most of the talks here, these systems are isolated, so there is no bath. And what we'll do is we'll take these systems out of equilibrium, far from equilibrium, and then there are several questions that we want to address. So we want to know how these systems evolve, what these dynamics depend on. We want to know whether these systems, these isolated systems, eventually equilibrate. And if it does, if the system does equilibrate, we want to know what kind of equilibrium is it. Is it thermal equilibrium or not? So this last question here is this the question is, do we have thermalization in these isolated many-body quantum systems? So since this is a workshop about quantum thermodynamics, I'll start from the bottom, and I'll use the bottom to motivate the main question that I'll be addressing here, which is really the dynamics. Okay? All right, so to talk about thermalization and to check whether a system thermalizes or not, there are two steps involved. First step is, first I need to guarantee that the system will equilibrate. So what do we mean by equilibration? So, and this is already what David was saying before. No? So I have my observable evolving. I'm going to write the initial state in terms of the energy eigenbasis here. I'm using all colors. No? So I'm going to write this initial state in terms of the energy eigenbasis, the eigenstates of the Hamiltonian that evolves the system. So you see that this observable depends on two terms. This first term here has no time dependence. It's just the components of that initial state. And these all alpha alpha, no, which are just the diagonal elements of that observable. The other term carries the dynamics. No, so this other term here has the components of the initial state, has the phases, and those off-diagonal terms. So what do we call equilibration? We'll say that this system equilibrates if after transient time, we will not have much effect of this anymore. My system, my observable, will be very close to this infinite time average. So this is what I'm trying to show in this plot here. No? There was a transient time, but after some time I have just these fluctuations around this dashed line, which is the infinite time average. Okay, so to talk, I don't know why it keeps moving. To talk about equilibration, we have to be sure that these fluctuations are small and that these fluctuations decrease with system size. So this is the first step. So when will this be satisfied? What I'm going to show here, what I'm enumerating here, are conditions that guarantees for sure equilibration. This is an extreme scenario. Do not need to go all the way there. But if I have this, for sure I have equilibration. So what is this extreme scenario? Well, first, if the eigenstates are random vectors. Now, if the eigenstates are random vectors, then those off-diagonal elements here, which show up there, will be very small. If my initial state is also a random vector, remember I'm dealing here with many-body quantum systems. No? So if my initial state is a random vector, I have many, many tiny components, which are random numbers, which are uncorrelated. And if my eigenvalues are non-degenerate, then these phases here will just lead to fluctuations, fast fluctuations, which on average cancel out. Okay, again, I repeat, I do not need this extreme case. But if I'm there, for sure, my system equilibrated. Okay, so equilibration in this sense that I'll be most time very close to this infinite time average. If we accept equilibration in this sense, then comes the second step. And the second step is I want to compare this equilibrium, this infinite time average, with a thermodynamic average. An average that I would obtain with a standard ensemble from statistical mechanics. Here we are using this microcanonical ensemble. If I have this equality between these two averages, then I'll say that the system thermalized. In practice, well, we don't have equal. No, what we are searching, what we are checking is whether these two sides are similar and whether, again, they get closer and closer as the system size increases. All right. If I go to that extreme case that I mentioned to you before, random vectors, for sure, this will be satisfied. Why? If I have just random vectors, all of my eigenstates are just random states. No? If I compute the expectation value, those O alpha alphas, no? Those diagonal elements, with one random vector or another random vector, of course, these results will be very similar. I just have small fluctuations that will decrease with system size. And so if I'm in that extreme case, for sure, thermalization is satisfied. Okay, now, when will I have this extreme case? With real systems, never. Okay, there is no real system where all of our eigenstates are random vectors. But with real systems, I can get close to this extreme case. And how do I get close to this extreme case? If I have chaotic systems. Okay? All right, so quantum chaos. How do we know whether a system, these isolated many-body quantum systems, is chaotic or not? I can look at static properties of the system. I can look at the eigenvalues, check if I have no degeneracies. I can look at the structure of eigenstates. And for realistic chaotic system, I do guarantee that I don't have degeneracies. I do guarantee that there is a region in the spectrum where my states are close to random vectors. And if I have an initial state probing those states that are almost random vectors, no? If I have an initial state that is perturbed very far from equilibrium, this initial state itself will be close to a random vector. Okay, so I know how to do that based on static properties, eigenstates, eigenvalues. What I want to do here is, I don't want to go to eigenstates and eigenvalues. I want to detect this quantum chaos. No? I want to detect these properties here that do guarantee thermalization in the dynamics. By looking just at the evolution of my system, can I say or not whether the system is chaotic? Okay? So this is a valid question. This is a valid question when if I don't have direct access to the eigenvalues or I have partial access to these eigenvalues. So what I want to discuss here is, well, if you look at the dynamics at short times and you have very fast evolution, for example, linear growth of the entropies, this is a signature that my perturbation was very strong, that I really took the system far from equilibrium. But this is not a direct signature of quantum chaos, so that's why I'm crossing. Okay? Where I'm going to find direct manifestations of quantum chaos in the dynamics at long times. At long times in the shape of what is known as correlation Hall, and this will be the main topic of this talk. We discussed a lot the correlation Hall in this paper here for different systems, different realistic systems. In this talk, I'll focus first on full random matrices. Okay? And why? Because this will give me analytical results. And then after that, I'll move to the realistic systems. Okay? So since we will be talking about full random matrices, let me introduce them here. So full random matrices were much used back in the 50s by Wigner, where he was trying to describe statistically the spectra of heavy nuclei, very complex systems. The idea is, well, instead of going for the details of these interactions between all these nucleons, well, just fill the matrix with random numbers. Much bigger than that, okay? This is just an illustration. Random numbers, and the only constraint of these random numbers is that they should satisfy the symmetries of the system we are trying to describe. So in our case here, I'm going to look at a matrix that is real and symmetric. Fine, it works very well. This describes statistically the spectra of these complex systems very well, but they are not realistic. Why? If it's completely filled like that, well, that implies that I have infinite range interaction, that I have all the particles interacting at the same time. But let me continue with them. That's the beginning, right? Some properties of these full random matrices. So I'm going to diagonalize this matrix, get all the eigenvalues, and I'm looking at the distribution on the histogram of the space in between neighboring levels. E2 minus E1, E3 minus E2, and so on. Make this histogram, we get this curve that looks like this red curve here, which is known as Wigner-Dyson distribution. The exact shape depends on the symmetries. But what is this distribution telling me? That there is no spacing, zero. In other words, I don't have degeneracies, That's one thing that I said would be good, right, for equilibration thermalization. So I don't have degeneracies. My levels do not cross. They repel each other. And level repulsion is one of the main signatures of what we call quantum chaos. So if I'm at the quantum level and I see level repulsion, if I see Wigner Dyson distribution, then if I bring my system to the classical level, I'll see chaos in the usual sense, Lyapunov exponent, extreme sensitivity to the initial conditions. So in this case here, where I have level repulsion, what I have is my spectrum becomes rigid. Now my eigenvalues are correlated. If my eigenvalues are uncorrelated, if my eigenvalues can cross, then we usually get distributions like this blue one, which is a Poisson distribution. All right? Okay, more properties about these full random matrices. If you just make a histogram with the eigenvalues, density of states, you get this semicircle shape. All right, how about the eigenstates? If I look at the eigenstates, they are all random vectors. No? So that extreme case that I told you about, no degeneracies, random vectors, I get with full random matrices. There are quantities that we can measure, that we can use to measure how much spread out, how much delocalized a state is. One of these quantities is the participation ratio. So I write my state in a certain basis. The participation ratio is 1 over the sum of these coefficients to the fourth. So you see if the state is very spread out, big superposition, many, many tiny C's, the participation ratio is large. If the state is localized, participation ratio is very small. For these full random matrices, all the states are random vectors. All of them give me the maximum value of the participation ratio, which is proportional to the dimension of the matrix, proportional to the dimension of the Hilbert space. These three here at the bottom comes from statistics.
Sorry, each dot there represents one eigenstate?
Yeah, each dot is an eigenstate. Here I put a very small system size. That's why you're seeing so big fluctuations. If you make it bigger and bigger, you see you get a straight line. No?
But these are eigenstates represented in the original basis of the matrix, right?
Yeah. Now, the basis, here I'm dealing with ensembles of random matrices, so the basis doesn't really matter. The basis is ill-defined, okay? But I have this flat distribution. All the states are equivalent. Okay, so properties of full random matrices, and now let me go for the dynamics with these full random matrices. So I'm going to look at the simplest quantity that we can think of, and then later I'll come back and give you some results for other observables that could be measured experimentally. So this simple quantity is just the overlap between the initial state and the evolved one. No? So this quantity here has different names. I'll be calling it survival probability. Just don't call it Loschmidt echo, otherwise Paula will be very upset at you, right? There is no echo here, but people now decide to call this Loschmidt echo. Yeah. Anyway, so if I write this initial state in terms of the energy eigenbasis, you see that the survival probability is just the sum of those components with those phases. I can also write this sum in terms of an integral, where this rho is just an energy distribution. Now, this rho carries this delta function. So it's an energy distribution, but not for the whole spectrum. It's the energy distribution for that particular initial state that I picked, so weighted by those components. So this distribution here, I'll call it local density of states because it depends on the initial state that I picked, LDOS. So you see, if I know this LDOS in detail, I know how the survival probability behaves. I just need to do this Fourier transform. Okay. So what I'm going to do, I'm going to pick an arbitrary initial state, and I'll let it evolve according to full random matrices. No? So I pick this arbitrary initial state, and I project into those random vectors. This is a theoretical exercise. No? It doesn't exist in nature. But why we are doing this? Remember, full random matrices give me random vectors. So I can random vectors and very correlated eigenvalues, and these correlations have been very well studied. So with those features, I can get analytical results. So that's the purpose. So these will be analytical results that will give me bounds for the dynamics, analytical results that I can use as reference to the studies of realistic systems. Okay, so I looked at picked my arbitrary initial state. I'm projecting to random vectors. First thing that I want to do is look at the energy distribution, the LDOS for that initial state, and what I get, again, the semicircle shape, just as the density of states. What I need to do now, the Fourier transform of this semicircle, and we know how to do that. You get this analytical expression here. This I1 is a Bessel function of the first kind. So this is an analytical expression, which I'm showing here with the solid line, and agrees very well with the numerics, which are these circles. So we are happy. What do we see here? First, very fast, abrupt decay, and then those partial revivals. If you study these oscillations, the envelope of these oscillations numerically, or if you study this expression asymptotically, you see that this decay here goes as T2 minus 3. Now, so I have a Power-law decay, even though here I have a super chaotic system. It's again giving me a Power-law behavior. Where do we get this 3 here, the Power-law exponent? It depends on the tails of my LDOS. Okay? In this case here, the LDOS goes abruptly to the bounds of the spectrum, and this is what originates this exponent 3. So, good, we are happy, but I'm not telling you the whole story. Because I chopped my plot, if I show you the plot for longer times, this analytical expression will go all the way to 0. But the numerics will saturate at an infinite time average now at a finite value. Okay? So this analytical expression is not picking this saturation point. The other thing that this analytical expression is not taking into account is, well, I just did the Fourier transform of the envelope. I'm not looking at what is inside. I'm not looking at the internal structure of this distribution. So there are two things that I have to look more carefully: the saturation point and what is inside this distribution. Okay, so let me continue. So this is the expression for the survival probability. I have this squared, which I'm going to open. So instead of a single sum, I now have two sums in alpha and beta. This first term, again, as we talked before, is the term that gives me the dynamics, controls the evolution. This second term is when alpha and beta are equal, so has no time dependence. This is the saturation. So you see the saturation depends just on how spread out my initial state is in the energy eigenbasis. This sum we've seen before. This sum is the inverse of the participation ratio. Now, so this saturation value, I know what it is for full random matrices, for random vectors. This is just that 3 divided by the dimension of the Hilbert space of the matrix. So this saturation point is this dashed line that I'm showing here. Okay. Let me go back to the dynamics, the term that gives me the dynamics. Within this term, there is actually 2 terms. I'm not going to show you the math. I can show you slides later. But inside this term, we have 2. One is that envelope, the Fourier transform of the envelope, which gave us that Bessel function. The other term that is contained here is what I'm calling this B2 function. What is this B2 function? This is the term that captures the internal structure. This term here only exists if I have correlated eigenvalues. Okay, so this function here, this function here only exists if I have a Wigner-Dyson distribution or something between Poisson and Wigner-Dyson. If not, if my eigenvalues are uncorrelated, if I have Poisson distribution, this term disappears. Okay? This, I'm going to come back to each term, but this is the analytical expression for full random matrices, which controls the whole dynamics from the moment I took the system out of equilibrium all the way to equilibration. So let me compare this analytical expression with numerics. So here in red, I have my analytical result, and in black, I have the numerics. And you see, you cannot distinguish the 2 curves, no? So very good agreement. So let me go again through each one of these terms. Short time is controlled by Fourier transform of the envelope. And what do we have here? This abrupt decay and those partial revivals that decay as T2 minus 3. Very long time, I have the saturation, which I'm showing here with this dashed line. In between the two, the term that controls the dynamics is that B2 function. Okay? So let's discuss this B2 a little better. What is this B2 doing? Well, the vessel is trying to go to 0, and the B2 carries it up to the saturation. So this B2 creates this dip, this drop below the saturation point. This dip here is what is known as correlation hole. And I repeat, this correlation hole will only show up if we have level repulsion. Only show up if we have something close to a Wigner-Dyson distribution. This is a true manifestation of quantum chaos, direct signature of quantum chaos that I find in the dynamics. What comes before, very fast dynamics, I can also have in integrable systems. The whole I cannot have in integrable models. Okay? So the correlation hole was studied some time ago. Well, the first time that was proposed was in 1986 in the context of molecules. So it was studied very early on by some chemists. Paul Broomer has studies on that. And why did it show up there in chemistry? The problem with molecules is that you may not have very good line resolution. And then you cannot do level spacing distribution. No, you cannot just play directly with the eigenvalues. So the idea of this French group is, let me do a Fourier transform of this spectrum. And that's where this idea of the correlation hole came up. It was then also much studied among the quantum chaos community, Al-Hasid, Weider-Müller, Seligman. They also studied this correlation hole a lot in the context of full random matrices. What we are trying to do here is we are trying to bring this subject to these realistic systems that can be studied experimentally. This correlation hole, let me just mention this. This dip here is also showing up now, is being revived in these studies about laws of information in black holes, in these SYK models. And there they call this correlation hole the ramp. And Adolphe is here. He has a very nice study comparing those studies about the SYK model and the survival probability. Okay, so this is just an aside. You can talk with Adolfo later. Very well. So what I said is I want to bring this subject to realistic systems. I want to look at realistic systems and extract the signatures of chaos. I want to extract what is generic to quantum chaotic systems. So for that, I'm going to focus on one-dimensional models of spin half. And why these particular models? Because, well, it can describe many realistic systems, many experiments like the ones done with NMR, with cold atoms, and with ion traps. And in this talk, I'm going to focus on just 2 Hamiltonians. Remember, I said we have results for many other Hamiltonians. But I'm going to focus on this Hamiltonian here, which we call XXZ model. So what is it that we have? Well, sigma Pauli matrices, okay? So we have couplings in the X and in the Y direction, same strength, and couplings in the Z direction, and only couplings between near state. So this Hamiltonian here, known as XXZ model, is integrable. It can be solved with the Bayesian ansatz. So if you look at level spacing distribution for this Hamiltonian, usually, in most cases, you're going to get Poisson. So yeah, the levels can cross. So this is an example of an integrable model. As an example of a chaotic model, I'm going to pick a Hamiltonian that looks very similar to that one. I still have the XXZ part, but I'm going to add on-site disorder. Now, so on each site here, I have a different Zeeman splitting randomly distributed. So depending on the values that I pick for this disorder, this system is chaotic and will give me a very nice Wigner-Dyson distribution. Okay. All right, some properties for these spin systems, for the static properties of this system. Now, so first, level repulsion, which is similar to what we had for full random matrices. I had full level repulsion for the full random matrices. I have level repulsion for these realistic chaotic systems. Well, what are the differences? We said full random matrix completely filled. Well, spin systems, the matrices are very, very sparse. What are other differences? The density of states. Instead of semicircle, in systems where I have two-body interactions, many body quantum systems with just two-body interactions, the shape is Gaussian. What else? Yes.
What's the distribution for the HM?
For what?
The field, HM.
Field? It's the same. It doesn't matter. This shape here.
No, the disorder, H.
Yeah, so any model that has just two-body interaction will give me this Gaussian shape.
No, go back a sec. The H sub n.
The distribution. What's the
Okay. It doesn't matter. I'll be using here uniform. Uniform. This is between minus h and h. But you could use from a Gaussian distribution also. It doesn't matter. No? It just has to be random numbers. There are studies for this kind of Hamiltonian with correlated disorder also. But I'm not going to go into that. Okay. So uncorrelated. Okay. So the density of state Gaussian, and then the other thing is the eigenstates. So remember the eigenstates of full random matrix, they're all random vectors. For these realistic systems, what we find is close to the middle of the spectrum, my eigenstates can be very much spread out. I can have very large values of the participation ratio. I can have states that are close to random vector, but at the edges, no. Okay, so there is this important energy dependence. So if you go back to what we are talking about thermalization, well, for these realistic systems, I can have level repulsion, lack of degeneracies, and I can have states that are close to random vectors, but in a region of the spectrum, as I had said. All right, so these are the properties, static properties. Let me go to the dynamics. Remember, we are looking at this survival probability. So what we are going to do is, I'm going to start with initial states such as this one. Now, on each side, the spin either points up or down in the z direction. And I'm going to let initial states like this evolve with the disorder Hamiltonian. I'm going to do averages over many different disorder realizations. Yeah, so you see here, this is minus h to h, random, uniform.
Between H and J?
You will see. I will go through that. Yeah. I will check many different values, very small h, large h, and so on. So, but I'm going to be doing averages over different disorder realizations, and I'm also going to do averages over different initial states, different configurations, such as this one. So, as you were asking, first thing that I want to do is describe, characterize this Hamiltonian depending on the h and depending on the j. So let's do this first. So this is something that we did long ago in 2004. And what we did there was to describe level statistics. I'll tell you what this eta is, but level statistics, to describe the level of delocalization of the eigenstates. We also studied entanglement, but forget about this part. I'll just focus on these two plots. So this eta that I'm showing here is defined with this equation. What this eta is telling me is the number, the value of this eta will tell me if I'm close to Wigner-Dice or if I'm close to Poisson. When h is 0, so here, so then I have just the xxz integrable model, this eta gives me 1. That means integrable. As this h increases, what I'll have is my Poisson distribution will get more and more and more deformed until I get a Wigner-Dice down here. If I keep increasing this disorder, so now this disorder, this h, gets larger than the coupling strength, then I'll see that I'll get out of this chaotic region and move into another integrable point. Let me make a parallel between level statistics and the level of delocalization of the eigenstates. And for this now I have to choose bases, no? Because I'm dealing with realistic systems, the bases here matter. I'm going to choose as basis those computational basis vectors, not those states that I'm using as initial states. When h is 0, my states are still delocalized, still spread out in this basis, so I have a reasonable value of this participation ratio. As h increases and I go to the chaotic region, the participation ratio increases even more, becomes proportional to the dimension of the Hilbert space, indicated that my eigenstates are becoming close to random vectors. Let me keep increasing this h, and if I keep increasing this h, then what we see is that our eigenstates will become more and more localized. More and more localized, and indicating that I'm reaching another integrable point is a point where I have localization in space. Okay. Between this chaotic region and localization in space, if I look at the eigenstates, well, they're in between the two extremes. No? The participation ratio is dimension to a power, where this power is smaller than 1. Okay, so now this is all static. Let me go for the dynamics. Remember what we're doing? I'm starting with initial states such as this, and let it evolve with this Hamiltonian. What I'm doing here in the language of quench, no? I'm basically starting with the easing part. This is an eigenstate of the easing part. And I'm changing this Hamiltonian dramatically. Now I'm adding those x, x, y, y. I'm adding the flip-flop term. I'm adding the hopping term to this Hamiltonian. So this is a scenario of very strong perturbation. Very strong perturbation. If I look now, remember what I have to look at is the energy distribution of the initial state. No? If I look at the energy distribution of the initial state, I get a Gaussian shape in this limit of very strong perturbation. Gaussian shape, which is a reflection of my density of states. No? So this is energy distribution of my initial state, has this Gaussian shape just as the density of states. But to get that, I need very strong perturbation. So remember, the survival probability at short times is controlled by the Fourier transform of this envelope. Fourier transform of a Gaussian gives me a Gaussian decay. And this is what you see here with these dots. So this initial decay is Gaussian. But later, you see many different curves showing up. You see decays, the decay is slowing down. You have these oscillations here. If you study the decay of these oscillations, you will see that you have a Power-law behavior. Okay? Now let me explain all these different curves. Each curve here corresponds to a different value of the disorder of this H. Okay? All right, so you see that I separated these curves into red and green. So let me start with the red. The red curves here correspond to the region where I have good Wigner-Dyson distribution, when my eta is very much below, where my system is very close to chaos. Now I have good level repulsion. So this is the red region. Now, when I have chaotic system, the eigenstates are pretty close to random vectors. So this is the scenario where the disorder is small. And if I look at these Power-law exponents, I have large values of this Power-law exponent larger than 1. Okay, how about the green region? In the green region, what we have is level spacing distribution between Wigner-Dyson and Poisson. This green region corresponds to this intermediate scenario where I'm leaving the chaotic region and going into localized phase. So in this intermediate region, I have strong disorder. My eigenstates are not random vectors anymore. This D2 is smaller than 1. Okay? And if I look at the Power-law exponent, it's smaller than 1. Yeah.
The intermediate region, the time scale over which you reach the average value seems to diverge. Do you have some way of quantifying that?
The saturation?
Yeah.
I'll come to that. There is one more step before saturation, which is the correlation hole. Okay, but I'll come to that. Let me compare all of these different curves with the energy distribution of the initial state. So here I'm looking at that LDOS, the energy distribution of the initial state for different values of H. Small h, chaotic region, what I have is that Gaussian distribution very well filled, that my initial state is close to a random vector. Now it's filling the energy shell. As I increase the disorder and my eigenstates are becoming more and more localized, you see that my energy distribution, my LDOS, is becoming very sparse. Okay? All right, so now what I want to discuss is the values of this Power-law exponent. In this region here, remember what I said, the Power-law exponent is smaller than 1. what we found out, now what we saw is that the value of this power law exponent agrees with this D2. So this is a nice result. Huh? The D2, I just get from studies of the static properties, not just the eigenstates of the system, my initial state. So I do scaling analysis, I get this D2. And this D2 agrees with this power law exponent. So this D2 or this power law exponent, they are the same thing. What they are telling me is that my eigenstates are not random anymore. These components are not random numbers anymore. These states are becoming correlated. And the level of correlations between these components is measured by that power law exponent. Okay? Oh, we're already finishing? Yeah? Okay. All right, so this D2 is called fractal dimension. How about the red region, the chaotic region? Well, in this red region, what is the source of my power law decay? Very similar to what we had with full random matrices. The power law decay for full random matrix is controlled by the bounds in the spectrum, how I approach the bounds in the spectrum. Here's the same story. I also have bounds in the spectrum, but I approach them slower. If I take it, when I'm doing my Fourier transform, if I take these bounds into account, now I have the Fourier transform of this Gaussian. If I take the bounds into account, I get Gaussian decay with something else, with these arrow functions. If I study this asymptotically, I get power law exponent 2. Hossein, how many minutes do I have? Okay, fine. So, okay, so then I'll go just quickly, and maybe you can ask me. Now, I'll just say, because the purpose of the talk was to talk about the correlation hole. Okay, so I'll slow. But in this panel here, yeah. To fill the hole, yeah. So at long times, if my system is chaotic, I'll see the correlation hole, which I said is the true manifestation of quantum chaos. H.5 here is strong chaos for the system size that I'm studying, and you see the hole there. As I put this H smaller and smaller, going into the clean integrable model, the hole disappears. The other direction, if I put this H larger and larger, going to the other integrable point of localization space, again the hole disappears. No? So this is a direct signature of chaos in the dynamics. Well, there is more to say, but let me just finish with one idea. Remember, for full random matrices, I had a complete analytical expression that described my whole dynamics. I want the same for my realistic system. So by following the same steps, by making an analogy, we propose this expression. So what do I have here? Remember, for full random matrices, I had Bessel with that power law exponent 3. Well, here I'm proposing a Gaussian with power law exponent T2 minus 2. Let me say I'm trying to get an expression for the chaotic system. No? So Gaussian T2 minus 2. Later, I had the correlation hole. I'm going to use the same function that I used before, and then the saturation. This expression here has a single fitting constant, and you see very good agreement with the numerics. Okay? So the whole description of the evolution. At long times, I'm using the same function that I used before, meaning at long times, we don't care about details of the models anymore. We only care about correlations between the eigenvalues. So these are all the curves there together. And let me just finish with this sentence. The correlation hole is not exclusive to survival probability. It shows up in observables also. This is an observable measured with cold atoms. This is the hole. As the disorder increases, it disappears. It appears also in the out-of-time order correlated and other observables. So, yeah. So, thanks for your attention.